Hello, student, and welcome to this chapter or chapter what is lattice dynamics. And now I am going to explain what are these crystal or lattice directions. Actually, it is not my part, but this knowledge is required uh, in the future chapter. So, what you are looking is a cube. The cube is there at this corner of the cube. We have fixed a three-dimensional coordinate axis. So therefore, this is the x-axis, this is the y-axis, and this is the z-axis. And what are these crystal directions? So these crystal directions are the directions which are passing through some particular point of this lattice or this some unit cell. So the direction which is passing through this atom or which is passing through the which is passing along the x-axis is called is referred as a 100 direction. So here 1 refers to x coordinate actually. So that indicates that this direction is a 100 direction. Similarly, this y direction is referred as the 010 direction, and this z direction becomes the 001 direction. And some other direction, suppose if you are coming along this direction which passes through this atom, so this is 110 direction, because here this is the xy plane. So this atom is in the xy plane, so therefore the coordinates of x and y are there, the z coordinate is 0, so therefore this is called as the 110 direction. So this is 011 direction, yz plane, and this is 111 direction which is passing through this corner atom, because this atom belongs to all the axes, all the planes, or it is at the middle of this three-dimensional coordinate axis, so all coordinates are there, therefore this is called as the 111 direction. So this part you have to write, I will show here to write, this small addition is there. So this is the actual topic. We are considering wave motion in one-dimensional monatomic lattice. A one-dimensional monatomic lattice is shown in this diagram. Lattice, the meaning of lattice means it is a three-dimensional arrangement of the atoms in a periodic way in this space. It is called as the lattice. So one dimensional in this is one dimensional monatomic lattice. Here we have considered the atoms which are of same kind, and we are looking at only one dimensional motion, means along the x-axis. So these are the atoms, and all atoms are separated by a distance of e. At rest, this is the position. The atoms are in this position, and when some external energy is supplied, these atoms starts vibrating, and when they are vibrating, let us say these are the displacement of the atoms along x-axis. So every atom, all atoms shifts toward in the positive x direction in this way. You can see here they are displaced from their position. So therefore, let us consider a one-dimensional monatomic lattice of atoms along x-axis. M be the mass of the atom. The small m is the mass of all atoms, and they are separated by each other by a. Here a. Every atom is separated by a, or the distance between two nearest neighbors is a. Like it is, therefore it is automatically the lattice parameter. In the solid state language, it is called as a lattice parameter. So the small a is a lattice parameter. In a cubic crystal, when a wave is moving along 100, 111, and 110 directions, all atoms so vibrate in phase. So that is why I explained what are these 100, 111, and 110 directions. So in this diagram, uh, 100, 111, 110. So these are the directions. So when a wave, let us wave is moving along these directions, all atoms vibrate in phase. In phase means all will go up and come down at a time. That kind of vibration is called as a in phase vibration. So we consider the motion of a longitudinal wave in 100 direction just for simplicity. Okay. So let dash 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 xn minus 1 xn plus 1 dash 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 are the displacement of atom when excited. So this I explained here. So xn minus 2, xn minus 1, xn plus 1, xn plus. So these are the displacement of the atoms from their mean position when they are excited. So uh, so displacement of atoms so when excited, we assume that only neighboring atoms interact with each other. Only nearest neighboring atoms. That means this atom interacts with this. This will not interact with this. That is the meaning of nearest neighbors. So this atom will interact with this atom, and this atom will interact with this atom. So this much interaction will be there. This atom will not interact with this atom or this atom. So the meaning of nearest neighbors means that one. Only the adjacent atoms interactions will be along with the adjacent atoms. So here you have to put a one paragraph which is here. This is the paragraph. Okay. So the interatomic forces due to n plus 1 and n minus 1 atoms are acting on nth atom. So again, you look at this diagram here. Here nth atom is there. So this is the nth atom. The interatomic forces due to this atom and this atom will act on the nth atom. So that is the meaning. So the interatomic forces are due to forces due to n plus 1 and n minus 1 atoms are acting on the nth atom. It is assumed that these forces are proportional to the relative displacement of the atoms. Hence, it is called as an harmonic approximation, and the force is said to be in elastic limit. So it is assumed that these forces are proportional to the relative displacement. That means you are in the elastic limit. Hooke's law. We can say that these vibrations are verifying the or obeying the Hooke's law. So that is the meaning. So that this this paragraph you substitute here, you write here before this start. So therefore, we assume that the vibrations are harmonic in nature as the forces are within the elastic limit. And the force acting on nth atom is given by using spring relation or Hooke's law. F is equal to minus kx is called as a spring relation, or it is also called as the Hooke's law. F is equal to minus kx. F is the force and x is the displacement. Within the elastic limit, the applied force is proportional to the displacement. So that is the meaning of Hooke's law. So, or the spring relation. We have used the spring relation here. So this is written as F is equal to beta into x plus 1 minus xn minus beta into xn minus xn plus xn minus 1. So here x is equal to minus ks form is there, f is equal to minus kx form. But here two forces are there which are which are acting opposite to each other. For example, this is the nth atom. One force because of this n plus atom is acting in this direction, and another force because of this atom n minus 1 is acting in this direction. Since these two forces are opposite to each other, there will be some net force or the resultant force acting on this atom n. So that is written in this way. That is why minus sign here. These are the two opposite forces and which are acting, which are parallel and opposite forces. So negative sign. The resultant will be the negative. We have to subtract those two forces to get the resultant. So in this way it is written, and you simplify this bracket, you will get this one. It becomes xn plus 1 plus xn minus 1 minus 2xn, like this. F is equal to, and now according to the Newton's second law, you replace this f with m into d square xn divided by dt square. Newton's second law, f is equal to ma is there. Use that. So this LHS of this equation 1 can be written as m into d square xn divided by dt square is equal to this RHS beta into this much. So this equation 2 represents the motion of nth atom. This equation 2 represents the motion of the nth atom. We may solve this equation by considering the solution of the type, this type action is equal to a into exponential of I into the bracket omega t minus kNa. Okay. So this is the solution of the expression 2, and where a is the amplitude, and it is also actually a wave equation. It gives displacement of the wave equation, and where k is equal to 2 pi by lambda. This is as explained in the last class. It is a wave vector or the propagation vector, and the x coordinate of the nth atom of the chain is n into a. That is xn is equal to n into a, because we have considered a one dimensional chain of n atoms. It contains n number of atoms. Okay. So next, and now you differentiate equation 3. Differentiate equation 3 once, it becomes dx by dt is equal to a into I omega exponential of I into omega t minus kNa. Differentiation of equation 3. It is so it is e raised to ax form. Differentiation of e raised to ax is a into e raised to x, that form. So this I omega comes, and again you differentiate this equation again. Once again, it becomes d square xn divided by dt square. This is equal to a into I omega whole square, because again I omega comes, so it multiplied, it becomes square, and this thing is there, and this is equal to minus a omega square exponential of I into omega t minus kNa, because this negative sign comes because of this I square, which is a complex number. I square is equal to minus 1. Again, from equation 3, we have xn plus 1 is equal to a into exponential of I into omega t minus k into n plus 1a, from equation 3. So equation 3 is there. Wherever n is there, just you put n plus 1, you will get another equation. So that is done. In place of n, we have written n plus 1. So this is the equation, xn plus 1 is equal to this much. And again you put n is equal to n minus 1 in place of n. Wherever n is there, you put n minus 1, we will get another equation. So you together let this is 5, and now we have to substitute equations 3, 4 and 5 into equation 2. Equation 2 is there, m into d square xn divided by dt square is equal to beta into this much is there. So we have to substitute this the value of this d square xn divided by dt square and xn plus 1 and xn minus 1 and xn in this equation 2. All the values are available here. Xn is there, d square xn by dt square is there, and these two xn plus 1 is there, xn minus 1 is there. Substitute all the values in the equation 2. Equation 2 comes like this. After substituting all the values. And now we have to cancel a into exponential of I into omega t minus k n a on both sides, because here a into exponential of I into omega t minus k into n plus 1 into a is there. So here two terms are there. When you are multiplying this a with this bracket, it becomes minus k n a and minus k a. So two terms are there, and one term is this one, k n a term is there. So that will be cancelled. That will be cancelled from this, and here also this term is there, omega t minus k n a term is there in this bracket, that is also cancelled, and this term is completely cancelled as it is the same term. So after cancellation, what is left is that this much is left, minus m omega square is equal to beta into exponential of minus ika plus exponential of my plus ika minus 2. This much is left after cancellation. And we can make use of the trigonometry here. So trigonometry, using trigonometric formula, this much is 2 2 cos ka. This much is 2 cos ka, and 2 is also here, so that 2 comes outside, and what is left in the bracket is cos ka minus 1, and this is equal to 2 beta into cos ka minus 1 from trigonometry is minus 2 into sin square ka by 2, and this negative sign is now is there on both sides, it is minus m omega square, and this much is there, negative sign is cancelled on both sides, and you take m to RHS, this equation becomes omega square. Omega square is equal to 4 beta divided by m, because this 2 is multiplied to this 2, giving 4. So 4 beta, and this LHS m comes to RHS, it goes down. So it is 4 beta divided by m into sin square Ka by 2. This one. Or we will write this equation taking root on both sides. It becomes omega is equal to root of 4 beta divided by m into sine of Ka by 2. So this one important equation we got here, and this is called as the dispersion relation. So because any relation which connects omega and k in solid state physics is generally called, or in solid state physics or in other some physics, it is generally called as a dispersion relation. Because this equation also relating this omega and k, therefore this is called as a dispersion relation. So we got the dispersion relation for lattice vibrations of a monatomic lattice. And here, where this omega m is equal to root of 4 beta upon m, this quantity. So in equation 6, this quantity is there, it is a constant, root of 4 beta upon m, that is represented as omega m, and that is called as the natural cutoff frequency of the vibrations. And this dispersion relation is plotted. This dispersion relation is plotted as shown below, and this is the dispersion relation. So this is the dispersion relation, and we have plotting actually omega divided by root of 4 beta upon m versus sine of that thing. Actually, this is a graph of omega divided by root of 4 beta upon m into sine of ka by 2. That is plotted, and this kind of curve is obtained. And you look at this curve. This curve is like this, and the range between this minus pi by a and plus pi by a is called as the first billion zone. So this is the first billion zone, and the range between plus pi by a to 2 pi by a and minus pi by a to minus 2 pi by a is called as the second billion zone, and so on, as you know it. So for the property wise, the only the first billion zone is very very important one, because it is assumed that the first billion zone is showing all the properties that are exhibited by a crystal or a lattice. So then whatever the other zones are there, they are just the replica of the first zones. And now the lattice acts as a low pass filter here, because uh, the lattice do not allow the frequencies which are greater than omega m is equal to root of 4 beta upon m. So because we have plotted here omega divided by root of the 4 beta upon m, then omega becomes equal to this much, this becomes 1, the quantity becomes 1. So that is, therefore that is the maximum limit for omega. Omega cannot exceed this value. So therefore this lattice acts as a low pass filter. Low pass filter means that is the, actually in electronics it is an electronic circuit which allows a certain range of low frequencies and cuts all the higher frequencies. That is the meaning of low pass filter. So this monatomic lattice is behaving as a low pass filter. That is the meaning. So even and what happens if omega m becomes greater than that value? It goes imaginary again. Therefore, because of that reason, the omega starts decreasing exponentially. So therefore, so omega m corresponds to here. Omega m corresponds to the point of maximum amplitude of this wave. So that is the highest displacement of this wave also. So today is this much, and we'll continue.